So I do have a quick comment or question for everybody before we get started. So again, while grading homeworks, it appears that people are still Googling or ChatGPT or something. It's either that or this is the most sophisticated linear algebra class I've ever had with the proof techniques that are being used. So honest question, would you prefer me to stop collecting grading homework? I can still give you problems for practice. I'm still happy to get feedback and post answer keys, but it is literally a waste of everyone's time if you're just going to copy down something off the internet. I'm dead serious. I'm happy to keep grading, but I want to grade people's actual work, not what's on the internet, because it's literally a waste of everyone's time. The whole point of the homework is not to earn points. It's to get ready for exams. This is why I collected to be able to give you feedback, right? So, serious question. I mean, do you want me to stop collecting grading homework? I'll still give it. I'll still hand it out. And you can come still ask me questions. I'll still post answer keys. I'll even, if you want to turn it in and have me give it feedback because you worked on it, I'm fine too. But I don't want to continue grading internet crap. It doesn't help me at all. It doesn't help you at all. So, honest question. What would you rather me do?
That's like that what you just said.
You want me to stop collecting grading homework?
Yeah.
Okay. Is that fine? I'm serious. I'll do it. I mean, I don't care one way or the other. We can just not have it count your grade and just have your grade based on exams. I'm okay with that. Yeah.
You should have a secret ballot.
Well, we have a secret ballot. Yeah, absolutely. You can email me your preference if you'd like. Just let me know.
We still have website, right?
You just have the web assigned because that's more computational stuff and a little bit of concepts, right?
Yeah. Oh yeah.
But you can just email me your preference. That's fine. But I literally want to know because, again, like I said, it's just a waste to grade things that are copied off the internet. For everybody. There's not any point in you taking the time to do it at that point. You're not getting anything out of it. All right. Just let me know. I mean, like I said, I'm happy either way. That makes me zero difference. I just don't want to grade things that are clearly, well, should be correct if it's if somebody actually did it correctly on the web, but it's not helping you get the information out of it. It's not the point of it. So, in any event, to that end, are there any questions about anything? We're going to finish up inverses today, and we're going to talk about elementary matrices today, which have to deal with inverses, and the elementary matrices are also going to give us another way to solve a system of equations that may be more computationally efficient in certain situations, which is the whole reason why we're going to talk about it. All right. Well, let's look at this example. We talked last time about how we can solve a system of equations. I actually talked last time about a general method for finding inverses and talked about how we can solve the system of equations if we know the inverse. If we know the matrix has an inverse, then we can solve the system by multiplying the constant vector matrix, if you will, by the inverse of the coefficient matrix. So first, if I want to write this as a matrix equation, how would we write it? So that would be as an augmented matrix, right? So as a matrix equation, I have the negative 1, 3, 5, negative 14. We would multiply it by xy, good. And on the right-hand side, we'd have 6, negative 2. And again, if we know that the matrix has an inverse, we can multiply both sides by the inverse to get rid of this matrix on the left-hand side and do the product on the right-hand side, and that'll give us our answers, right? Since we have a 2 by 2, how can we find the inverse relatively quickly? So what formula do we use? Okay, 1 over AD minus BC. What is the AD minus BC in this case? What would you do? 14 minus 15, good. So if I look at this matrix here, I'll do it off to the side. you would do negative 1 times negative 14 would be 14. 3 times 5 would be 15, right? Okay. And then what do we multiply by?
14.
Say it again.
14, negative 3.
Okay, so we do negative 3, and then it'll be negative 14, right? We flip the main diagonal and negate the off diagonal, so that'd be negative 5, and this will be negative 1. And then since that's negative 1 on bottom, we distribute it all the way through. Our inverse would be 14, 3, 5, 1 in this case. And you can check your answers, right? It's one of the nice things about calculating inverses. You can check your answers relatively quickly just by multiplying by the original matrix. So if we multiply both sides by the inverse, then our answer would be 14, 3, 5, 1 times 6, negative 2. We get 84 minus 6, so we get 78. I did my arithmetic correctly. 30 minus 2 is 28. Right, relatively larger numbers, but we can always check our answers, right? Just plug it back into the original system. So, pardon me, we can do this relatively quickly if we can do the inverse relatively quickly. Depends on the matrix, right? We know for 2 by 2s we can do the inverse relatively quickly, do that multiplication, and we can get the answer. If we can't get the inverse relatively quickly, then there might be a better way to do it from a computational standpoint. Also, this only works if the matrix is invertible, right? If the matrix doesn't have an inverse, then you'd have to do row reduction anyway to get at it. That okay? Let's do the next example here together. Make sure that we remember how to do inverses of matrices. So, pardon me. Let's do the next example, and then we'll go through the algorithm for finding the inverse and solve this one. So, I want to set this up as a matrix equation. What would the matrix equation look like?
So, 2, negative 1, 4.
Okay.
4, negative 1, 8. And negative 1, 1, negative 3.
Okay. And we'll multiply that by
X, Y, Z.
Yeah, I got give different variable names that time. And on the right hand side, we'll have
1, negative 3.
Good. Okay. All right. So again, if we're going to use this technique that we're talking about, I need to be able to figure out the inverse of this matrix and then multiply both sides by it to cancel it off the left-hand side, and we'll have the answer left on the right-hand side. Remember, again, multiplying by the matrix inverse is kind of like dividing by it, right? All right. So again, we'll need to use our technique for finding the inverse of a 3 by 3 or any larger square matrix. We don't have a nice little trick like we do for the 2 by 2, right? So what do we do instead? Yeah, augment the identity and row reduced, right? Or maybe alternative number 2 would be put in your calculator. All right, so we're going to put the coefficient matrix on the left-hand side, augment the identity on the right-hand side. First step is to get what? Yeah, 1 in the upper left-hand corner, right? What might you do to get a 1 in the upper left-hand corner?
Divide it by 2.
I can divide it by 2. That'll put some fractions in there, right?
Yeah.
Okay. Is there a way to do it without avoiding some fractions? Yeah, I could add row 3 up to row 1 and replace row 1, right? That'll eliminate some fractions to start with. You can absolutely divide row 2 by 2, or excuse me, row 1 by 2. You could absolutely do that as your first step. That's perfectly fine. Just put some fractions in there and might make it a little nastier for the arithmetic. So it's easier in this case to add just add row 3 to row 1, not negative for row 3. And replace row 1, just add up. We'll get 1, 0, 1. Oh, for heaven's sake. And then 1, 0, 1.
Wait, no. Oh, yeah.
Yep, okay. Always should check my arithmetic. All right, next step is to do what? Get zeros below, good. So what do I need to do to get a 0 right here? Good. Multiply the first row by -4, add to the second, replace the second. To get a 0 right here, down there in the lower left corner, what do we need to do? Good. Row 1 plus row 3 and replace row 3. Good. Again, that does not change the first row at all. What do you get in the second row? Well, the first number in the second row should definitely be 0. Good. And then the third row becomes what? Good. By the way, if you've got your TI-84s, there are row operations built into those as well. You can actually do each of these operations on your matrix on your calculator if you're worried about the arithmetic. The syntax is a little screwy here and there, but if you want to know how to do that, just come see me and I'll show you how to do it on your calculator. That part okay? Okay. Next step is to do what? One in the middle. And I see 2 relatively easy ways to do it. Doesn't matter which one you do. What are the 2 ways that you could do it? Yeah. Take the negative of row 2. What else could you do?
2 row 3 plus, or 2 row 3 plus.
Yeah, you could do it that way too. What's the third way? Just flip row 2 and row 3, right? You could, right? Just swap. Don't forget your row swaps, right? Yeah, I could literally just swap them, right? Doesn't matter what it does not matter which one you do. There's just more than one way to get there. And actually, you could do 2 times row 3 and add it to row 2 if you really wanted to. That was a third way, probably more complicated than the first 2, right? Literally doesn't matter. What you do not want to do is work with row 1 to try to get a 1 here, because then you're going to mess up that first column. All right. So which one would you rather do? Swap them? Okay. Like I said, literally does not matter what you do, so we'll just swap them. So the second row becomes 0, 1, -2, 1, 0, 2. And the third row becomes 0, -1, 4, -4, 1, -4. Again, as long as you do legitimate row operations, doesn't matter how you do it. What's next? Good. Row 2 to row 3, replace row 3. So the only thing we're changing at this stage is row 3. What does row 3 become?
0, 0, 2, -3,
Okay. So far, so good? Now at this stage, we don't really have a choice. We will have to divide to get that to be a 1. Again, I don't want to, I'm at my last row. I don't want to try to use previous rows to get a 1 here because it'll mess up this column, these 2 columns that you already did. Okay? So the only thing I can do here is divide everything by 2 in row 3. So 1/2 row 3 replace row 3. So the first 2 rows stay exactly the same. The second one becomes 0, 0, 1, negative 3/2, 1/2, negative 1. Almost there, almost home. Two more operations to do. What's the first one? Yep, I need to do row 2, 2 row 3 plus row 2, replace row 2. What else do we need to do? Okay, good. I gotta get both of these to be zeros, right? All right, doesn't change row 3. What does row 1 become?
1, 0, 0.
Something. 5/2. Minus 1/2. 2. Good. Yeah, I agree. Row 2 becomes
0, 1, 0. 6 over 2, 3. So 2.
I think it's negative 2, isn't it?
Yeah, negative 2.
Okay.
1.
Okay. 0. Okay. All right. So the inverse of our original matrix is that piece right there, right? Okay. I'm going to, so I don't have to rewrite it, I'm just going to grab it. I'm going to cheat and grab it because I don't feel like rewriting it. All right. So the inverse of 2, negative 1, 4, 4, negative 1, 8, negative 1, 1, negative 3 is that matrix, right? That part okay? Are we okay? Are we comfortable with the row operations to get to that point?
Yes.
Okay. And again, if it were the case that you got to a point where you had a row of zeros on the left-hand side of your augmented bar, what would you say about the original matrix? It's non-invertible, which is the same thing as singular, right? Yeah. Good.
Yep. You said if.
Yep.
Is that one time?
Is that if you get a row of zeros in that left-hand side, if you get a row, that left-hand side piece, then it's not invertible. It's singular. Okay. Yeah, I'm talking about the inverse part. Yep. Yeah. If you get a row of zeros as you're doing it, then you just say the matrix is not invertible. Yeah. All right, so the last part then for this particular problem is we want to solve it. So what is your x1, x2, x3 going to equal as a product first, and then we'll simplify it. Yep, the inverse times, good, yep, the inverse times the constants that we have. So I'll multiply that matrix we just found by the constants that are on the right-hand side. And let's see if we can do that. 5/2 plus 3/2 is 8/2. So we get 4. Negative 2 minus 3 is negative 5. Negative 3/2 minus 3/2 is going to be -3. I did my arithmetic right. And again, since it's a system of equations, you should be able to check because you can plug those numbers in and see that it works in all three equations. How do I get a small matrix? I'm taking a 3x1, or excuse me, a 3x3 times a 3x1, so I end up with a 3x1. Right? Because my first row entry is that times that. I don't have any more columns to go to. So there's only one column in the product. Right? Because it's a 3x3 times a 3x1. The answer will be a 3x1. Other questions on that one at all? I'll leave the next one for you for practice, as well as the application problem that I put in there. I think there was an application problem somewhere. But here at the end, I have something that I'm referring to as mega theorem. All right, what I would encourage you to do with this is write this on a separate sheet of paper somewhere and keep that separate sheet of paper handy because we're going to come back to it. We're going to have like 20 parts of this theorem by the time we're done with the semester. Okay? So I would encourage you to put this on a separate sheet of paper so that and know where it is so that you can reference it later. Okay? I'm not kidding. There will be probably 20 parts to this theorem. Okay? By the time we're done with the semester. All right? All right. So, what do I mean by mega theorem for this stage? Well, the fact that it has 20 parts to it is what makes it mega. All right? Notice that the statement of this particular theorem says the following are equivalent. What that means mathematically is that if I assume any part, I can prove any other part. That's what it means to be logically they are equivalent to each other. They say the same thing. Okay? So far, pardon me, we've got several answers, or several things that are equivalent. I think I've got 4 going to be listed here so far. All right, so the first one is that A is invertible. That's statement 1. Okay. So what we're going to do is we're going to collect a whole bunch of statements that are equivalent to A being invertible. Okay. So the first one that we'll say is equivalent, which we've already seen, and that's with solving those matrix equations, is that I can say that this matrix equation AX equals B has a unique solution for all B. Since I'm talking about an n by n matrix, our B will have n, it will be an n by 1. So I'll even write n by 1 matrices here on the end, B. No matter what constant vector we put on the right-hand side of the equation, we always get a unique solution. But it turns out that we can even say something a little bit less strict. N times 1. It's a column. It's an n by 1. Okay. There, I can make it look like a fancy one. It's enough to just say that this is consistent no matter what. It's enough to say that. Think about why, and this is going to be what the fourth one is. In that previous example, the way we solved the matrix equation, we found the inverse of the matrix by row reducing, right? If it's going to be invertible, when you row reduce, what does the form of the reduced row echelon form have to look like? What matrix do you have to get when you do the reduced row echelon form when you're done, if it's going to be invertible? The identity, right? Remember that was our whole point, right? We augmented with the identity matrix and we row reduced until we solved the identity matrix, right? Well, if I always row reduce to get the identity matrix, it doesn't matter what you put on the right-hand side. You're still going to get the identity matrix, which means I can always solve it. right? So consistent is good enough. Just turns out that consistent here is also unique at that point. Okay? All right. Well, the last one is exactly what I just said. You just told me that when you row reduce, you get the identity, right? So the last one that's equivalent here is the reduced row echelon form of A is the identity. That's the last thing that's equivalent to it. We're going to add more of these things later on. As a matter of fact, we'll have one at the end of the next section. But this kind of makes sense because especially this last one is exactly what we do to find the inverse, right?
Yeah.
You stick A in a matrix and you row reduce it, and you hope to see the identity matrix, right? All right. So let's go on to our next topic. I'll leave that application problem at the end for you for practice. Let's go on to this concept that we're going to refer to as elementary matrices. All right. So the first thing we notice in my definition that I have started there at the top of the page, notice that it says that we're talking about an n by n matrix, right? So automatically, elementary matrices have to be square, right? So we don't talk about non-square elementary matrices. Well, what do we mean by elementary matrix? What we say is that this is elementary if E is one elementary row operation away from the identity. Okay? Again, it's going to depend on the size of the matrix. So elementary matrices could be 2 by 2 or 3 by 3 or 4 by 4. So we're talking about it being exactly one elementary row operation away from the identity matrix for that particular size. Remember we had 3 elementary row operations. What were they? Swap rows, that's 1. You could, do a multiple of one row and add it to another. Third one was multiplied by a constant, non-zero constant, right? Right? So look at this first one. So the 2 by 2 identity matrix is 1, 0, 0, 1. Is this one row operation away from the identity? Yes. What did you do to the identity matrix, or vice versa? What can you do? What one operation can you do to this matrix to get back to the identity? Yeah, 2 row 2 added to row 1, right? That'll get you back to the identity, right? So it's one row operation away, right? One row operation away, okay? So the first one here is elementary. Yep.
Because you can multiply row 2 by 2.
Yep. Yeah. Yeah. So it is elementary. It's an elementary matrix. Okay. Because if we do 2 row 2 plus row 1 replace row 1, we get the identity, right? One row operation, right? Or again, vice versa. It depends on which way you want to think about it. If I start with the identity matrix and do -2 row 1 added to row 2, vice versa. -2 row 2 added to row 1 and replace row 1, I get that matrix, right? So you can think about it either way. Start with the matrix and get back to the identity, or start with the identity and get to that matrix in one step, right? It has to be one step. If it's more than one step away, then it's not elementary. Does that make sense? Okay. Next matrix, is that elementary? No, what's wrong with it? Yeah, notice that it looks like I could have taken the identity matrix and multiplied row 2 by what? 0. Is that an elementary row operation? No. Okay. In fact, elementary matrix. In fact, is there any elementary row operation that you can do to this matrix and get it back to the identity? No. Because there's nothing that you can do to that matrix to make a pivot right here. Right? Nothing we can do. So this is not elementary. Okay? What about C? Now, what was the first thing I said had to be true about elementary matrices? It had to be squared, right? So this one's not elementary. Oops. I guess I should probably provide a little bit of a reason in the previous step. We can't get a pivot in row 2. Right. How about D?
Yes.
What row operation can you do to that matrix to get back to the identity? Yep, good. So this is an elementary matrix. Say it again. Yeah, so that's exactly what we're doing. We're multiplying by the negative 1/5. Yep, that's right. Yep, you're right. What about the last one? Is that one elementary? No. If you wanted to get back to the identity matrix, how many row operations would you have to do? 2, right? I'd have to do 2 row operations to get back to the identity, right? Because I need to make this a 0 and that a 0. So you'd have to do 2 row operations to get back, right? Okay. So that one's not elementary because it's 2 row operations away. And again, elementary matrices require you to be 1 elementary row operation away, not 2. Okay. Does that make sense? All right. Why do we care? Good question. All right, so let's see what happens when we multiply. And in particular, on the left, we're going to take all of these examples are multiplying our matrix on the left by an elementary matrix. What 1 row operation did you do to the identity matrix to get to that elementary matrix in the first example? Swap the rows, right? What happens when you multiply? What do you get? What matrix do you get when you multiply? Yeah. You get C, D, A, B. Good. What happened in the result? Yeah, just swap the rows again, right? So notice that you have this row swap here in your elementary matrix. You multiply it by this one, and it does the same row swap. So notice that the row swap in the elementary matrix does the row swap. So you can accomplish row swapping by matrix multiplication. Okay? All right. Let's look at the next one. Why is that a matrix on the left an elementary matrix? Yeah, we can divide by negative 1/2 for the third row, or we could take the identity matrix and multiply by negative 2, whichever way you want to think about it. start with the identity, get to that matrix, or vice versa. Thinking about with starting with the identity matrix, we've multiplied row 3 by -2. Right? That was the elementary row operation we did. Okay? What do you get when you take this product? What do you get in the first row? Good. 2, 1, 3, -1. What do you get in row 2? I'm going to skip a row for the time being. What do you get in row 4? Good. Notice that those rows didn't change at all, did they? Okay. What happens with row 3? It's just multiplied by -2. Good. So now ignore the elementary matrix and look at these two. What elementary row operation would you have done to get from that matrix to that matrix? Yeah, -2 row 3 and replace row 3, right? So that elementary row operation, again, is accomplished by this multiplication by the elementary matrix.
I'm not following. I thought you divided 1/2.
To get back to the identity, you would divide by a -1/2, right? But again, think about what you did when you started with the identity. If you start with the identity, what would you do to get to here?
Oh, times by -2.
Me too. Okay, so that goes from that matrix to that matrix. What did you do? Multiply by -2. Yep. Okay. All right. Last one. Why is the matrix on the left elementary? Yeah, so again, if I start with the identity matrix, you would do 3 row 2 added to row 1, replace row 1. What, right? If I started with the identity matrix, it's 3 row 2 added to row 1.
Yeah.
Yep. Okay. Do the product. What do you get? Well, let's do the last 2 rows to start with. What do you get in the last 2 rows?
0, 1, 0, 5.
Good. Notice the last 2 rows don't change, right? Because the 1 in the middle matches with the middle row. The one in the one in the corner matches with the bottom row. What do you get in the first row?
1, 0.
Okay. Okay, so if you take row 2 by 3 and add up, you get 3 times 1 plus -3. Yeah. So I'm just literally doing the multiplication. I'm just doing the multiplication here. Yeah. You're right. If I were trying to get this back to the identity, I would take this times -3 and add up, right? But think about it the other way. Get from the identity of this matrix is 3 times it, right? So the same idea here. All right. So the last entry would be 3 times -2 is -6 plus 3 is -3. Okay. So it has the exact same effect.
So you wouldn't try to multiply the left side, try to get the identity, you multiply it.
Yeah, we're just multiplying through at this point. Yeah, we're literally just multiplying through. Yep. All right. Now, let's ignore the fact that I did matrix multiplication for the time being. And just concentrate on this matrix. Notice I've already got a 1 here in the upper left-hand corner and zeros below it, right? And then I've got a 1 right here in the middle. It looks like I'm in the middle of trying to row reduce this matrix, right? Doesn't it? All right, the way it's set up, the way I put it, I did that on purpose. Every once in a while, I do things on purpose. Okay. Start with a 1 here, get zeros below it. We get a 1 here. Then what your next step would be to get zeros above and below it, right? How would you get a 0 above? You would take 3 times row 1, or row 2, added to row 1, and replace row 1, right? That's exactly what would be the next step. I can accomplish that by doing the same matrix multiplication with an elementary matrix. Okay? So say you wanted to continue. Say you wanted to do the row reduction. What would be your next step? Yeah, I do -5 row 2 plus row 3, replace row 3, right? What elementary matrix could you use to accomplish that? Okay. 1 0 0 0 1 0. Yeah, 0 negative 5 1. Right. That's the row operation you would do to the identity matrix. Right. If you did negative 5 row 2 and added to row 3 and replaced row 3, what do you get when you multiply? I get the same first row. I get the same second row. Then I do negative 5 times 1 plus 1 times 5 gives me 0. Negative 5 times negative 2 is positive 10 plus 8 gives me 18. Right? So that would be the next step in the row operation. This is going to pop up, by the way, when we have a different method for solving systems of equations when I wasn't talking about it. Okay. So what's the point? Yes. It's literally the exact same row operation that you would use if you were row reducing. So again, if I want to make this 0, I would do negative 5 row 2 added to row 3. Right? Negative 5 row 2 added to row 3 puts a negative 5 right there. That's how we know. Okay. So the next one, what would we need to do to this 18? Divide by 18, right? Multiply by 1/18. So what elementary matrix would you multiply on the left to make that into a 1? 1 0 0 0 1 0 0 0 1/18. We put a 1/18 in the corner. Yeah. Okay. That's exactly what we would do. All right. So what's the summary here? Yeah, you're trying to get a pivot. Yep. So multiplication on the left, that's important on the left, by an elementary matrix does the exact same row operation as is done to create that elementary matrix. Whatever you do to the elementary matrix to make it an elementary matrix, right? Start with the identity, do the row operation. If I multiply that elementary matrix times another one, it accomplishes the exact same row operation. It does literally the same thing. That's the whole point. Okay. All right. Pardon me. All right. So notice that, and we've talked about this already, if I start with an elementary matrix, can I always get back to the identity? Yeah. So every single elementary matrix is also invertible, no matter what, right? So just to write that down, all elementary matrices. Oops. What's that? Nope. We will have one going on the mega theorem later, but nope, this is just still in the notes. Yep. All elementary matrices are invertible. Right. What are their inverses? That's what I've got the list here. What are their inverses? Well, what are your 3 elementary row operations again? Row swap. How do you undo a row swap? Swap it back. Do the exact same row swap again, right? So this is an example here. If I had 1 0 0 0 0 1 0 1 0 and I wanted its inverse, what would be the inverse of that matrix? Now, is that the inverse? I think you just said this was the identity, right? You just said the inverse of a row swap is literally the same row swap. So what would be the inverse of this matrix? It's the exact same matrix. Yeah, good. Right? It's literally the same thing. Remember, what did we just say on the previous page? When I multiply by an elementary matrix, it accomplishes the same row operation, right? So what did you say you had to do to undo a row swap? Literally do the same swap, right? So I need to multiply that matrix by itself to do the two swaps back to back.
Oh,
Yeah. Okay. So it literally is itself. The inverse of a row swap is a row swap. It's literally the same thing. So just write that off to the side. I'll call it E1 is the elementary matrix with row I and row J swapped. Then the inverse of E1 is just itself. And you can check that. If I multiply those two matrices together, I get the identity matrix. Right? Notice that if I think about where they match up, if you do row 1 and multiply it across, I get 1, 0, 0. If I take row 2 and multiply it across, notice I get 0, 1, 0 in the right spot. And same thing with row 3. What's another elementary row operation? Multiply a row by a constant, right? So let's say you had 1, 0, 0, 0, 0, oops, 0, 1, 0, 0, 0, 3. And I wanted to do its inverse. How did I create that elementary matrix? What did I do to the identity to get to that one? Multiply by 3. I need to undo that. So instead of multiplying row 3 by 3, I need to multiply row 3 by 1/3. So what should its inverse be?
1/3.
Good. Should look almost exactly the same except with the reciprocal on the bottom. Because again, if I take this matrix, which multiplies row 3 by 3, I need to undo it by multiplying it by 1/3. When I multiply it together, I get a 1 in the lower left-hand corner. So to write this off to the side, I'll call it E2, is the elementary matrix with row I multiplied by C. Then E2 inverse is the elementary matrix. Oops. With row I multiplied by 1 over C. Same row operation, just we had to flip the constant, right? So think about, for a second, what if I had 1, 0, -5, 1, and I wanted to undo that? What row operation did you do to the identity to get that elementary matrix that I wrote down? Good. -5 times row 1 added to row 2, replace row 2. I need to undo that. So what matrix should you end up with to undo it? I gotta undo adding by -5. 1, 0. I agree with the 1, 0 part. I'm adding in this case. How do I undo addition by -5? Yeah, add 5. Yeah. Okay. So we'll summarize that next time, and we'll talk more about elementary matrices. Again, please do email me your preference of whether or not you want me to continue collecting homework for a grade, or you'd rather just me give it to you and you can do it for practice. I'm happy either way. But again, what I really do not want to do is grade problems off the internet, grade solutions from the internet, right? It's a waste of time. Okay, really a waste of my time. Frustrates me. So just let me know. Email me your preference. Again, I'm happy either way. I'm happy to continue grading and give you feedback. And if we decide not to count it for a grade, but you still want feedback, I'm happy to do that too. Okay, but I want to grade your work, not someone else's work. Pointless. All right. Have a good one. We'll see you on Friday, if not before. Some of you I see tomorrow, but